Alrighty, I'm back. So, now we get to talk a little bit more about some interesting topics here, like concurrency and parallelism. Throughout the history of digital computers, two demands have been constant forces in driving improvements. We want them to be more, and we want them to run faster. We want them to do more, and we want them to run faster. Let me just swing this bad boy over here. Give me some more light so I can see. Okay. Both these factors improve when a processor does more things at once. We use the term concurrency to refer to the general concept of a system with multiple simultaneous activities, and the term parallelism to refer to the use of concurrency to make the system run faster. Parallelism can be exploited at multiple levels of abstraction in a computer system. You might highlight 3 levels here, working from the highest to the lowest level in a system. In the system hierarchy, thread level concurrency. Building on the process abstraction, we are able to devise systems where multiple programs execute at the same time, leading to concurrency. With threads, we can even have multiple control flows executing within a single process. Support for concurrent execution has been found in computer systems since the advent of time sharing in the early 1960s. Traditionally, this concurrent execution was only simulated by having a single computer rapidly switch among its executing processes, much as a juggler keeps multiple balls flying through the air. This form of concurrency allows multiple users to interact with a system at the same time, such as when many people want to get pages from a single web server. It also allows a single user to engage in multiple tasks concurrently, such as having a web browser in one window, word processor in another, and streaming music playing at the same time. Until recently, most actual computing was done by a single processor. Even if that processor had to switch among multiple tasks, this configuration is known as a uniprocessor system. So that's kind of what I grew up on. When we construct a system consisting of multiple processes all under the control of a single operating system kernel, we have a multiprocessor system. Such systems have been available for large-scale computing since the 1980s, but they have more recently become commonplace with the advent of multi-core processors and hyperthreading. Figure 116 shows the taxonomy of these different processor types. Multi-core processors have several CPUs, referred to as cores, integrated into a single integrated circuit chip. Figure 117 illustrates the organization. So we got this diagram down here categorizing different processor configurations. Multiprocessor are becoming prevalent with the advent of multi-core processor and hyperthreading. So you got all processors, and then you get 2 categories. You got uniprocessors, and then you got multiprocessors, which are a different set. Inside that you have multi-core and hyperthreaded, and you can have multiple core hyperthreaded. You have a combination of the two. I think that's SMT. Hyperthreading is SMT. Okay, over here we got multi-core processor organization. 4 processor cores and are integrated into a single chip. So we've got cores 0 to 3. Each one has their own registers. L1 Dcache and L1 iCache. And then L2 unified cache. L3 unified cache shared by all cores, and then main memory. I think there's separate fetch, decode units, separate ALUs. There's a lot more to the core than just what they're diagramming here. Sorry, I'm on the right page. What's interesting is that, oh, there it goes. Yeah, there's a lot more in that to the CPU than what's in this diagram. But yeah, this diagram illustrates the organization of a typical multi-core processor where the chip has 4 CPU cores, each with its own L1 and L2 caches, and with each L1 cache split into 2 parts, one to hold recently fetched instructions, and one to hold data. The core share higher levels of cache as well as interface to main memory. Industry experts predict that they will be able to have dozens and ultimately hundreds of cores on a single chip. Hyperthreading, sometimes called simultaneous multithreading (SMT), is a technique that allows a single CPU to execute multiple control flows. It involves having multiple copies of some of the CPU hardware, such as program counters, register files, while having only single copies of other parts of the hardware, such as the units that perform floating point arithmetic, whereas a conventional processor requires around 20,000 clock cycles to shift between different threads. A hyperthreaded processor decides which of its threads to execute on a cycle-by-cycle basis. It enables the CPU to take better advantage of its processing resources. For example, if one thread must wait for some data to be loaded into the cache, the CPU can proceed with the execution of a different thread. As an example, the Intel Core i7 processor can have each core executing 2 threads, and so a 4-core system can actually execute 8 threads in parallel. Use of multiprocessing can improve systems performance in 2 ways. First, it reduces the need to simulate concurrency when performing multiple tasks. As mentioned, even a personal computer that being used by a single person is expected to perform many activities concurrently. Second, it can run a single application program faster, but only if that program is expressed in terms of multiple threads that can effectively execute in parallel. Thus, although the principles of concurrency have been formulated and studied for over 50 years, the advent of multi-core and hyper-threaded systems has greatly increased the desire to find ways to write application programs that can exploit the thread-level parallelism available within the hardware. With the hardware. Chapter 12 will look much more deeply into concurrency and its use to provide a sharing of processor resources and to enable more parallelism in program execution. Instruction level parallelism. This is something I learned from the Stanford class that I kind of audited last year. I didn't really complete the whole class because I didn't do any of the exercises. But I was doing some of the reading and the lectures and recitations and stuff like that. But I learned about instruction level parallelism. Which is things like pipelining, having separate. Yeah, I think it's just like kind of like pipelining. We have separate threads of execution. I don't know. To be honest, my brain mapped it onto SIMD, and clearly SIMD is a different section on this page. So let's go and just read about it, because clearly those neurons have faded. At a much lower level of abstraction, modern processors can execute multiple instructions at one time, a property known as instruction level parallelism. So is that the capability of like doing fetch decode while you're doing like ALU stuff, while you're doing floating point stuff? Like you have all of the different components of the CPU actually doing work at the same time? Maybe that's what that means. For example, early microprocessors such as the 1978 vintage Intel 8086 required multiple, typically 3 to 10 clock cycles to execute a single instruction. More recently, processors can sustain execution rates of 2 to 4 instructions per clock cycle. Any given instruction requires much longer from start to finish, perhaps 20 cycles or more, but the processor uses a number of clever tricks to process as many as 100 instructions at a time. In Chapter 4, we will explore the use of pipelining, where the processor hardware is organized as a series of stages, each performing one of these steps. The stages can operate in parallel, working on different parts of different instructions. We will see that a fairly simple hardware design can sustain an execution rate close to 1 instruction per clock cycle. Processors that can sustain execution rates faster than 1 instruction per clock cycle are known as superscalar processors. That's where that term comes from. So it's a processor that can sustain execution rates faster than 1 instruction per cycle. Most modern processors support superscalar operation. In Chapter 5, we will describe a high-level model of such processors, we will see that application programmers can use this model to understand the performance of their programs. They can then write programs such as generated code. They can then write programs such that the generated code achieves higher degree of instruction level parallelism and therefore runs faster. So this is doing things like not branching. Because if you take a branch, you invalidate the instructions that were being speculatively executed in the pipeline. The pipeline stalls. You have to restart the pipeline. So to get avoid doing that, if you can avoid branches, you avoid branches. Single instruction, multiple data, SIMD parallelism. At the lowest level, many modern processors have special hardware that allows a single instruction to cause multiple operations to be performed in parallel. A mode known as single instruction, multiple data, is SIMD parallelism. For example, recent generations of Intel and AMD processors have instructions that can add 8 pairs of single precision floating point numbers. See data type float in parallel. These SIMD instructions are provided mostly to speed up applications that process image, sound, and video data. Although some compilers attempt to automatically extract SIMD parallelism from C programs, a more reliable method is to write programs using special vector data types supported in compilers such as GCC. We describe this style of programming in the website OptSIMD as a supplement to the more general presentation on program optimization found in chapter 5. Importance of abstractions in computer systems. The use of abstraction is one of the most important concepts in computer science. For example, one aspect of good program practice is to formulate a simple application programming interface API for a set of functions that allow programmers to use the code without having to delve into its inner workings. Different programming languages provide different forms and levels of support for abstraction, such as Java class declarations and C function prototypes. We got figure 1.9 here, some abstraction provided by a computer system. A major theme in computer systems is to provide abstract representations at different levels to hide the complexity of the actual implementation. So at the bottom level, you have things like I/O devices, main memory, the processor, the operating system, and then you got this little diagram here, which we've seen before, where the operating system okay, there's units of abstraction. Okay, we have already been introduced to several of the abstractions seen in computer systems as indicated in figure 118. On the processor side, the instruction set architecture provides an abstraction of the actual processor hardware. With this abstraction, a machine code program behaves as if it were executed on a processor that performs just one instruction at a time. The underlying hardware is far more elaborate, executing multiple instructions in parallel, but always in a way that is consistent with the simple sequential model. By keeping the same execution model, different processor implementations can execute the same machine code while offering a range of cost and performance. On the operating system side, we have introduced 3 abstractions: files and an abstraction of I/O devices, virtual memory as an abstraction of program memory, and process as an abstraction of a running program. To these abstractions, we added a new one, the virtual machine, providing an abstraction of an entire computer, including the operating system, the processor, and the programs. The idea of a virtual machine was introduced by IBM in the 1960s, but it has become more prominent recently as a way to manage computers that must be able to run programs designed for multiple operating systems such as Microsoft Windows, Mac OS X, and Linux, or different versions of the same operating system. We will return to these hardware isolation is good for security too. Number of benefits. I guess it wouldn't be hardware; it would be hypervisor level isolation. Anyways, we will return to these abstractions in subsequent sections of the book. Summary: a computer system consists of hardware and system software that cooperate to run application programs. Information inside the computer is represented as a group of bits. that are interpreted in different ways depending on the context. Programs are translated by other programs into different forms, beginning as ASCII text, and then translated by compilers and linkers into binary executable files. Processors read and interpret binary instructions that are stored in main memory. Let's reread that. Information inside a computer is represented as a group of bits that are interpreted in different ways depending on the context. Programs are translated by other programs into different forms, beginning as ASCII text and then translated by compilers and linkers into binary executable files. Processors read and interpret binary instructions that are stored in main memory. Since computers spend most of their time copying data between memory, I/O devices and CPU registers. The storage devices in a system are arranged in a hierarchy with the CPU registers at the top, followed by multiple levels of hardware cache, memories, DRAM, main memory, and disk storage. Storage devices that are higher in the hierarchy are faster and more costly per bit than those in the lower end of the hierarchy. Storage devices that are higher in the hierarchy serve caches for devices that are lower in the hierarchy. Programmers can optimize the performance of their C programs by understanding and exploiting the memory hierarchy. The operating system kernel serves as an intermediate process. Sorry, my nose is like scratching. Serves as an intermediary between the application and the hardware. It provides three fundamental abstractions. Files are abstractions for I/O devices. Virtual memory is an abstraction for both main memory and disk. Processes are abstractions for the processor, main memory, and I/O devices. Finally, networks provide a way for computer systems to communicate with one another from the viewpoint of a particular system. The network is just another I/O device. Okay. And we did all the problems already. Part 1. So I guess I can commit this, right? Yeah. Let's go back up to where we define the function. And just grab that bad boy. And we'll say problems. Spin up readme, and we're just gonna put a little X right there. Yeah. Okay. So we got our make file. Wait, okay. Makes sense. Do we have this test fun thing? We do not. So vim chapter 01 make file. We have test map pause and test stack recursion. So these guys are not needed. Bye, Felicia. Okay. CD chapter 01, make clean, make. Okay. Looks good. Okay, let's go back to our make file. Practice. Yep. Everything's good there. Test maps pause. Okay. Finish chapter 1. Okay, part 1, program structure and execution. Our exploration of computer systems starts by studying the computer itself, comprising a processor and its memory subsystem. At the core, we require ways to represent basic data types such as approximations to integer and real arithmetic. From there, we can consider how machine-level instructions manipulate data and how a compiler translates C program into these instructions. So compiler translates C programs. Okay. Next, we study several methods of implementing a processor to gain a better understanding of how hardware resources are used to execute instructions. Once we understand compilers and machine-level code, we can examine how to maximize program performance by writing C programs that, when compiled, achieve the maximum possible performance. We conclude with the design of the memory subsystem, one of the most complex components of a modern system. This part of the book will give you a deep understanding of how application programs are represented and executed. You will gain skills that help you write programs that are secure, reliable, and make the best use of computing resources. Chapter 2, representing and manipulating information. Information storage. So basically, we need to finish chapter 2 to advance in the lectures, because I think all this stuff is covered in the next couple lectures. All right. Modern computers store and process information represented as two valued signals. These lowly binary digits, or bits, form the basis of digital revolution. Familiar decimal or base 10 representation has been in use for over 1,000 years, having been developed in India, improved by Arab mathematicians in the 12th century, and brought to the West in the 13th century by the Italian mathematician Leonardo Pisano, better known as Fibonacci. Using decimal notation is natural for 10-fingered humans, but binary values work better when building machines that store and process information. Two-valued signals can readily be represented, stored, and transmitted, for example, as the presence or absence of a hole in a punch card, as a high or low voltage on a wire, or as a magnetic domain oriented clockwise or counterclockwise. The electronic circuitry for storing and performing computations on two-valued signals is very simple and reliable, enabling manufacturers to integrate millions or even billions of such circuits on a single silicon chip. In isolation, a single bit is not very useful. When we group bits together and apply some interpretation that gives meaning to the different possible bit patterns, however, we can represent the elements of any finite set. Sorry, let me reread that. In isolation, a single bit is not very useful. When we group bits together and apply some interpretation that gives meaning to the different possible bit patterns, however, we can represent the elements of any finite set. For example, using a binary number system, we could use groups of bits to encode non-negative numbers by using a standard character code. Using a binary number system, we can use groups of bits to encode non-negative numbers. By using standard character code, we can encode the letters and symbols in a document. We cover both these encodings in this chapter, as well as encodings to represent negative numbers and to approximate real numbers. We consider the three most important representations of numbers. Unsigned encodings are based on traditional binary notation, representing numbers greater than or equal to 0. To use complement encodings are the most common way to represent signed integers, that is, numbers that may be positive or negative. Floating point encodings are a base 2 version of scientific notation for representing real numbers. Computers implement arithmetic operations such as addition and multiplication with these different representations, similar to the corresponding operations on integers and real numbers. Computer representations use a limited number of bits to encode a number. And hence some operations can overflow when the results are too large to be represented. This can lead to some surprising results. For example, on most of today's computers, those using a 32-bit representation for data type int, computing the expression 200 times 300 times 400 times 500 yields 884 million, so on and so forth. This runs counter to the properties of integer arithmetic. Computing the product of a set of positive numbers has yielded a negative result. Oh, sorry, it's negative. I thought that was an EM dash. I didn't realize that was a negative sign. On the other hand, integer computer arithmetic satisfies many of the familiar properties of true integer arithmetic. For example, multiplication is associative and commutative, so that computing any of the following C expressions yields the same result. The computer might not generate the expected result, but at least it is consistent. Floating point arithmetic has altogether different mathematical properties. The product of a set of positive numbers will always be positive, although overflow will yield a special value positive infinity. Floating point arithmetic is not associative due to the finite precision of the representation. For example, the C expression d.14 plus 1 to the power of 22 minus, 1 to the power of 20 minus 1 e to. So basically you're adding this huge number and then removing it. It will evaluate to 0 on most machines, while doing the latter evaluates the correct value, which is 3.14. The different mathematical properties of integer versus float point arithmetic stem from the difference in how they handle the finiteness of the representations. Integer representations can encode a comparatively small range of values, but do so precisely. I mean, a 64-bit integer, that can encode a lot of freaking finite values. While a floating point representation can encode a wide range of values, but only approximately. By studying the actual number representations, we can understand the ranges of values that can be represented and the properties of the different arithmetic operations. This understanding is critical to writing programs that work correctly over the full range of numeric values and that are portable across different combinations of machines, operating systems, and compiler. As we will describe, a number of computer security vulnerabilities have arisen due to some of the subtleties of computer arithmetic. Whereas in an earlier era, program bugs would only inconvenience people when they happen to be triggered, there is now legions of hackers trying to exploit any bug that they can find. Am I on the wrong page? No, I'm on the right page. Oh, it's right here. Exploit any bug that they can find to obtain unauthorized access to other people's systems. This puts a higher level of obligation on programmers to understand how their programs work and how they can be made to behave in undesirable ways. Computers use several different binary representations to encode numeric values. You will need to be familiar with these representations as you progress into machine-level programming. In Chapter 3, we describe these encodings in this chapter and show you how to reason about. So this is very, very much a review for me. I mean, I've been using these representations for decades now, so I'm not going to get much out of this, but I'm going to get through it. We derive several ways to perform arithmetic operations by directly manipulating the bit-level representation of numbers. Understanding these techniques will be important for understanding the machine-level code generated by compilers in their attempt to optimize the performance of arithmetic expression evaluation. Our treatment of this material is based on a core set of mathematical principles. We start with the basic definitions of the encodings and then derive such properties as the range of representable numbers, their bit-level representations, and the properties of the arithmetic operations. We believe it is important for you to examine the material from this abstract viewpoint, because programmers need to have a clear understanding of how computer arithmetic relates to the more familiar integer and real arithmetic. A C++ programming language is built upon C, using the same exact numeric representations and operations. Everything said in this chapter about C also holds for C++. The Java language definition, on the other hand, created a new set of standards for numeric representations and operations, whereas the C standard standards are designed to allow a wide range of implementations. The Java standard is quite specific on the formats and encodings of data. We highlight the representations and operations supported by Java at several places in the chapter. Boop. Aside, how to read this chapter. In this chapter, we examine the fundamental properties of how numbers and other forms of data are represented on a computer and the properties of the operations that computers perform on these data. This requires us to delve into languages of mathematics, writing formulas and equations and showing derivations of important properties. To help you navigate this exposition, we have structured the presentation to first state a property as a principle in mathematical notation. We then illustrate this principle with examples and informal discussion. We recommend that you go back and forth between the statement, the principle, and the examples and discussion until you have a solid intuition for what is being said and what is important about the property. For more complex properties, we also provide a derivation structured much like a mathematical proof. You should try to understand these derivations eventually, but you could skip over them on the first reading. We also encourage you to work on the practice problems as you proceed through the presentation. The practice problems engage your active learning, helping you put thoughts into action. With these as background, you will find it much easier to go back and follow the derivations. Be assured as well that the mathematical skills required to understand this material are within reach for someone with a good grasp of high school algebra. Okay. Information storage. Rather than accessing individual bits in memory, most computers use blocks of 8 bits or bytes as the smallest addressable unit of memory. A machine-level program views memory as a very large array of bytes, referred to as virtual memory. Every byte of memory is identified as a unique number known as its address, kind of like an index into a big array. And the set of all possible addresses is known as the virtual address space. As indicated by its name, this virtual address space is just a conceptual image presented to the machine-level program. The actual implementation presented in Chapter 9 uses a combination of dynamic random access memory, DRAM, flash memory, disk storage, special hardware, and operating system software to provide the program with what appears to be a monolithic byte array. In subsequent chapters, we will cover how the compiler and runtime system partitions this memory space into more manageable units to store the different program objects. That is, program data, instructions, and control information. Various mechanisms are used to allocate and manage the storage of different parts of the program. This management is all performed within the virtual address space. For example, the value of a pointer in C, whether it points to an integer or a structure or some other program object, is the virtual address of the first byte of some block of storage. The C compiler also associates type information with each pointer so that it can generate different machine-level code to access the value stored at the location designated by the pointer depending on the type of that value. Although the C compiler maintains this type information, the actual machine-level program it generates has no information about data types. It simply treats each program object as a block of bytes, and the program itself as a sequence of bytes. Boop. Another aside, huge aside. Okay, the evolution of C programming language. As we described in a slide on page 40, the C programming language was first developed by Dennis Ritchie of Bell Laboratories for use with the Unix operating system, also developed at Bell Labs. At the time, most system programs, such as operating systems, had to be written largely in assembly code in order to have access to the low-level representations of different data types. For example, it was not feasible to write a memory allocator, such as is provided by the malloc library function. Let's reverse that because I was drifting, my mind was wandering. At the time, most system programs such as operating system had to be written largely in assembly code in order to have access to low-level representations of different data types. For example, it was not feasible to write a memory allocator such as is provided by the malloc library function in other high-level languages of that era. The original Bell Labs version of C was documented in the first edition of the book Brian Kernighan, Dennis Ritchie, by them, KNRC. Over time, C has evolved through the efforts of several standardization groups. The first major revision of the original Bell Labs C led to the ANSI C standard in 1989 by a group working under the auspices of the American National Standards Institute. ANSI C was a major departure from Bell Labs C, especially in the way functions are declared. ANSI C is described in the second edition of Carnegie Ritchie's book, which is still considered one of the best references on C. The Initial Standards Organization took over responsibility for standardizing the C language, adopting a version that was subsequently the same as ANSI C in 1990, and hence is referred to as ISO C90. The same organization sponsored an updating of the language in 1999, yielding ISO C99. Among other things, this version introduced some new data types and provided support for text strings requiring characters not found in the English language. A more recent standard was approved in 2011 and hence is named ISO C11. Again, adding more data types and features. Most of these recent additions have been backwards compatible, meaning that programs written according to the early standard at least as far back as ISO C90 will have the same behavior when compiled according to the newer standards. The GNU compiler collection can compile programs according to the conventions of several different versions of C language based on different command line options, as shown in Figure 2.1. For example, the compile program C according to ISO C11, you could give the command line so-and-so. The options ANSI and standard C89 have identical effect. The code is compiled according to the ANSI or ISO C90. So I've always heard it referred to as C89, but I guess it's also called C90. C90 is sometimes referred to as C89 since the standardization effort began in 89. The option standard C99 causes the compiler to follow the ISO C99 convention. As of writing this book, when no option is specified, the program will be compiled according to a version of the C based on ISO C90, but including some features from C99, some of C11, some of C++, and others specific to GCC. The GNU project is developing a version that combines ISO C11 plus other features that can be specified with the command line option standard GNU 11. Currently, this implementation is incomplete. This will become the default version. So we got C version 89, GNU 89, which is also ANSI, which is also ISO C90. And then you got ISO C99, which is a different effort, and then you got ISO C11. Next. Another aside. New to C, the role of pointers in C. Pointers are an essential feature of C. They provide the mechanism of referencing elements of data structures, including arrays. Just like a variable, a pointer has two aspects, its value and its type. The value indicates the location of some object, while its type indicates what kind of object, e.g. integer or floating point number, is stored at that location. Truly understanding pointers requires examining the representation and implementation at the machine level. This will be a major focus in Chapter 3, culminating in an in-depth presentation in Section 310.1, hexadecimal notation. Let's go ahead and make a directory here. KDR Chapter 02, CP Chapter 01. We're going to grab the make file and the dot get ignore, throw that into Chapter 2, CD make. Cool. Alright. Hexadecimal notation. A single byte consists of 8 bits. In binary notation, its values ranges from all zeros to all ones. When viewed as a decimal integer, its values range from 0 to 255. Neither notation is very convenient for describing bit patterns. Binary notation is too verbose. With the decimal notation, it is tedious to convert to and from bit patterns. Instead, we write bit patterns as base 16 or hexadecimal numbers. Hexadecimal, or simply hex, uses digits 0 through 9 along with characters A through F to represent 16 possible values. Figure 2.2 shows the decimal and binary values associated with the 16-bit hexadecimal digits, associated with the 16 hexadecimal digits. Written in hexadecimal, the value of a single byte can range from 00 to FF. In C, numeric constants starting with 0x or 0 capital X are interpreted as being in hexadecimal. The characters A through F may be written in either upper or lowercase. For example, we could write the number FA1D3B16 as 0x that number or 0x that number, or even mixing upper and lowercase. We will use the C notation for representing hexadecimal values in this book. A common task in working with machine-level programs is to manually convert between decimal, binary, and hexadecimal representations of bit patterns. Converting between binary and hexadecimal is straightforward, since it can be performed one hexadecimal digit at a time. Digits can be converted by referring to a chart such as that shown in Figure 2.2. One simple trick for doing the conversion in your head is to memorize the decimal equivalents of hex digits A, C, and F. The hex values B, D, and E can then be translated to decimal by computing their values relative to the first three. For example, suppose you're giving the number 1. Let me try this. Let's see. 173A4C. You can convert this to binary format expanded, each hexadecimal digit as follows. This gives the binary representation so-and-so. Conversely, given a binary number so-and-so, you'll convert it to hexadecimal by first splitting it into groups of 4 bits. Note, however, that if the total number of bits is not a multiple of 4, you should make the leftmost group be the one with the fewer 4 bits. Note, however, that if the total number of bits is not a multiple of 4, you should make the leftmost group to be the one with fewer than 4 bits. Yeah, obviously. Especially effectively padding the number with leading zeros. Then you translate each group of bits into the corresponding hexadecimal digits. Okay, let's do the stupid conversions. This will be 2.1, and then we say A, and then here it's going to be 0x25B9D2. Sorry, let me make sure that's right. 25B9D2. B is going to be 1010111001001001001. Take that to hex. Take this to binary. Let's see here, which is going to be. Actually, you know what? I'll just pull these things up here. I think that makes sense. 0x8b 3d to binary. And finally D, which is 110010001010, sorry, 10. I gotta type this again. I lost my track here. 11001010110010101010. Take that to hex. Okay. Alright. I mean, this is pretty simple to do, but I'll do it anyways. So let's take the value, we'll split out the nibbles. So each one of these is going to be 4 bits. So we'll just say, hey, 1, 2, 3, and then 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Then underneath here, I'm going to say 1, 2, 3, 4, 1, 2, 3, 4. Okay, 2, so it'll be 1 here. D, so D is, so we got 9, 10 would be A, 11 B. I guess I'll just type out the table here. A is 10. Oops. B, C, D, E, and F. B will be 11, 12, 13, 14, 15. I know F is all ones. 0, 1, 1, 2, 3. Come on, stop doing that crap. 4, 5, 6, 7, 8, 9. So those have literally the same values here. And then I'll just space these over a little bit to align them, and then we'll give these guys some extra space. And then over here, 1, 2, 3, 4. This would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's A is 1, 0, 1, 0. And he was talking about doing what numbers? Here we go. The hex values B, D, E can be translated by just choosing the values well to the first three. The first three are A, C, and F. So A and F are easy. A is 1, 0, 1, 0. F is 1, 1, 1. C would be 1. So 11 would be 1, 0, 1, 1. 1, 1, 0, 0. 1, 1, 0, 1. 1, 1, 1, 0. That. So C. So A 1, 0, 1, 0. That's pretty easy because A is 10, and you just say, hey, 10, 10. F is easy because it's all ones. And then C is like the midpoint between the two. So that's 1, 1, 0, 0. The B you can get just by adding 1 to A. D you can get by adding 1 to C. And then E you can get 1 by subtracting 1 from F. So I think that's what he was talking about doing. So 2 is that D, just looking at our lookup table. So C is going to be 1, 1, 0, 0. So D will be 1, 1, 0, 1. Yeah. 9 will be 1, 0, 0, 1. B will be 10, 11. Yeah. 5 will be 0, 1, 0, 1. I believe. Yeah. 2 will be okay. So I'm just going to take this here and just pipe it into Python. Say, hey, bin of this string, and we're just going to say, hey, is that equal to, and since Python has a binary literal syntax, I'm just going to yank this, say 0b, search for space, replace with underscore, and then yank that and paste it here. And I should say what? Maybe because the zeros, the padding. What I'll do is I'll say, hey, that, and then we'll do this here. I need to say bin of that. Bin of that and bin of that. And then we can easily diff these two. Yeah, they're equal. So I need to take the numeric form of it though. That's my problem. Instead of saying bin, I need to say just this. Oh, my bad. There you go, true. And I can have the padding in there too, because it doesn't affect the numerical representation. So we'll do that. Okay. Let's go ahead and delete this guy. Carry on here. Let's convert this binary to hex. So let's just grab that bad boy, paste it here. There we go. This will be A. This will be E. This will be 1, 2, 4, and this will be 9. I did that without looking at the table. So now we can say, hey, 0b, this value is equal to 0xAE49. That's true. Alright, so now we grab our hex value again here. Let's go ahead and dump it here. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And then we'll have 1, 2, 3, 4. Okay, A is 10, 10. 8 is of course that. B is going to be 10, 11. 3 is of course this. Oops. And D is 2 shy from F. So it's going to be 1, 1, 1, 1. But then you take one away, E. Take another one away, then you're going to go 0, 1 like this. I think that's correct. Yeah, D. So then I can yank, just to validate this, I'll yank that, put a 0b on it, and we'll search for space. We'll then replace with underscore, and we'll do the next one, bam, bam, bam. We'll say, hey, that is going to be equal to this value in hex. Bam. True. Okay, D. These are just like exercises. They're not really like super serious thinking stuff. Just to get some practice in. So I'm going to say A for everything just to get placeholders, even though it's not A. So this is, so obviously 3. This is 2. This is 2. So this would be 1 plus 4 plus 8, or 2, so that'd be F, E, D. 1101 is D, yep. And then we have 8 plus 1 is 9. And then we have 4 plus 2, which is 6. So we can say, hey, this whole thing here, yoink it. We say 0b, that thing is equal to 0x 322d96. True. Okay, those are pretty easy. All right, let's continue reading. When value x is a power of 2, that is, x is equal to 2 to the n, for some non-negative integer, n, we can readily write x in hexadecimal notation form by remembering that the binary representation of x is simply 1 followed by n zeros. The hexadecimal digit 0 represents 4 binary zeros. So for n written in the form of written in the form of I plus 4j, where I is, we can write x with a leading hex digit. I'm not understanding what you're saying here. When a value x is a power of 2, say 8, so that's 2 times 2 times 2 is 2 to the power of 3. That is, x is equal to 2 to the power of 3. For some non-negative integer, n, yes, we can readily write x in the hexadecimal notation form by remembering that the binary representation of x is simply 1 followed by 3 zeros. The hexadecimal digit 0 represents 4 binary zeros. So for n written in the form of I plus 4j, okay, so in this case j would be 0 and I would be 3, but say we had a power 2, maybe say it was x is equal to 2 to the power of 12, then it would be j would be 3 and I would be 0. So maybe we do like 9. So 9 would be j would be 2 and I would be 1. So where I is in between 0 and 3 inclusive, we can write x as a leading hex digit of 1. Yeah, 1, 2, 4, or 8. Followed by j hexadecimal zeros, sorry. As an example, for x is equal to 2048, which is 2 to the power 11. So we would have, in that case, 8 plus 3, so it would be 3. So you have an 8. We would have an 8 in the leftmost hex digit, and then we would have how many zeros? 2. So it'd be 822. Sorry, 8800. Yeah, that's correct. Okay. Practice problem. Fill in the blanks. We got some table. Okay, so we got 2 here. 2.2. Boom, 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 boom. 2.1, 2.2. Practice problem 2.2. Fill in the blank entries in the following table. Give the decimal and hexadecimal representations of powers of 2. So we have a table. I'm just going to do like let's generate a markdown table. Markdown table generator. Looks good. We have 1, 2, 3 rows, or 3 columns, and 1, 2, 3, 4, 5, 6, 7 rows. So this is going to be table 3 by 3, 4, 5, 6, 7. Table 4, 5, 6, 7. And I want no header. I guess I can just delete that manually. Whatever, I'll keep it. Why does this only have 5? Preview, generate, there we go. That's what I need. 1, 2, 3, 4, 5, 6, and then I guess I can make my own there. It's fine. Alright. So we dump in here, bam. And then if we go over to here, this is going to be n, oops, and then this will be 2 to the power n. Boom. And then here we'll have let's say decimal, and then this will be 2 to the power n hex. So let's go ahead and fill out the rest of this table. Whoops. Hey, got it right. First try. Alright. Oops. Wait a minute, I was wrong. There we go. Bam. Okay. So n will be our value here, which is 5. We got a 23 going on there. We got a blank, blank, 12. Okay, so let's fix these. Fix that. Pad that out. Put that there. Space that out. There we go. Okay, and then over in the decimal column, we have 5, 32. So that'd be 32. And then hexadecimal, I think I need to do the padding the other way. Let's just drop this whole column. Okay, hexadecimal will be 0x 2 0. So n is 5, which is 2 to the power n will be 32. 2 to the power n, and hex will be, so we have 32's divided by 4 how many times? Let's see, we got 8, 4, 8, 12, 16, 32, you got 5 zeros? Oh no, it's 2 to the power 5. 2 to the power 5, which means that we have 5 zeros. Which means it's 1. Should it be 1 0? For doing their algorithm from before? Oh, if I is equal to 0, then it's a 1. If I is equal to 1, it's a 2. Gotcha. That makes sense. Okay. So it just says here to fill in the blank entries in the following table, giving the decimal and hexadecimal representations of different powers of 2. Okay, let's finish filling out the values that they gave us. So 32,768. This will be 32,7. They got a comma there. This is a 2 as well. 32,768. Blank. This will be 0x 2 0 0 0. Okay. Then over here we got 12. Here's 64. So we got how many? 1, 2, 3, 4, 5, 6, 7. So that's 1, 2, 3, 4, 5, 6. So we need one more. And this is going to give us 0x100. 0x, oops, 100. Okay. Okay. Well, let's just do the table. So we got n23, 2 to the power of 23. Well, I know 2 to the power of 20 is a million something. It's a bit difficult to compute 2 to the power of 23 in your head. Does he expect us to do that manually? Let's just read the... Zoom out a little bit here. Converting between decimal and hexadecimal representation requires using multiplication division. All these conversion things, I understand like he wants us to get a little bit of practice with it. It's not gonna hurt anyone, but it's like, come on, bro, like computers do this so well. Alright, so we got 2 to the power n and decimal. I know it's 10, 20. It's gonna be like 8 million something, close to probably 9 million something. I don't know the exact value, so I'm just gonna have Python give it to me. So 2 to the power of 23. It's gonna be 9-ish million. Yeah, 8 million, a little over 8 million. So 8 comma 3 8 comma 608. And then over here in hex, blah, 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 blah. I guess we can go back to our table here. I'll just make this a little bit bigger here, because why not? What are you doing, bro? I hate it when this thing glitches out. Like, what? What is this? There we go. Alright, so we got our table up here. We're going to convert from decimal to hex. So I can go from hex to binary and binary to hex pretty easily. But going from decimal to any of binary or hex, I guess the path that I can do is decimal to binary to hex. The problem is that decimal doesn't line up well with like bits. There is no really like boundary where the bits, you have to do subtraction shit. So here, I mean, it's easier to do it like this and just say, hey, the binary representation of this is, since we already have n to the power 23. What is this? Why is that? Okay, whatever. So 2 to the power of 1 is 1. 2 to the power of 2 is... No, 2 to the power of 2 is 1. 2 to the power of 1 is 0. Huh? Let me rewrite that. 2 to the power of 1 is what in decimal? It's 2. 2 to the power of 0 is 1. 2 to the power of 2 is 4. How do you get the 0 value? Okay, I was gonna say, doesn't seem like it. Okay, so when writing out 2 to the power of n, this would come out as like 2 to the power of 0 would be 1. 2 to the power of one would be 1 0. To the power of 4 would be 1 0 0. 2 to the power of 3 would be 8, which would be 1 0 0 0. So these are our powers. So basically you take the power and that's how many zeros you get after the 1. If you're converting to hex, you divide that by 4. So to go to hex, we would have 1 to the power of 23. So that's pretty... I'm going to put like a little like asterisk next to this one because I didn't do it in my head. Asterisks. I calculated. Actually, you know, I did do that one in my head. Just okay. Let's do that and that. Bam. Oops. That. Okay, so getting back over here, we have 23. How many times can you put 2? Can you put 4 into 23? You got 4, 8, 12, 16, 20. So you got 3 left over. So you get 5 times 0. That's going to be 5 zeros. 1, 2, 3, 4, 5. And then you have a, what, 3 value left over, which will be an 8. Because it goes 1, 2, 4, 8. So I think it's that. If I do 0x, that is equal to 2 to the power of 23. True. Okay, here. Yeah, decimal isn't very convenient. I can see why people don't deal with it, who have to deal with this stuff regularly. I remember doing this in my undergrad, converting from decimal to binary to hex. So the best way I have to do it is just put like a bunch of zeros, and each one of these counts for 2 to the power of 1 subtracted from it. So you go all the way to the left. So I know this would be 1, 2, 4, 8, 16, 32. Well, 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096. Eight, 16, 32. So it's gonna be 1 here. I know it's gonna have a 1 there. I think this is the actual binary representation. Yeah. Okay, so that's binary. Chunk it up like that. Well, we have how many zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this will be 2 to the power of 15. And over here to the power of this in hex. So we're going to have 3 sets of zeros here. And then we have a nibble of 8. So it'd be 800. Yep. Okay, so now we're taking this down to a 2. So 8, 4, 2. You go down to here. So that's a new value. So 1, 2, 4, 8, 1632, 6428, 256, 512, 1024, 2048, 4096. So I don't even have to, yeah. It'd be 4096. 4096 times 2, because this would be 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, and then you got one more bit. So you have to do the math on this. This is the one that I don't really remember off the top of my head. So 6612. So you carry the 1. 99 is 18, 19. So this is going to be R9, carry the 1, 1, and 8. So this will be the decimal value. And I'll put a comma in there for funsies. And then to convert that into hex, or to estimate how many ends there are, so that's 2 to the power of 1, 2 to the power of 2. No, 2 to the power of 1 goes here. 2 to the power of 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's going to be a 12 here. Wait a minute. That's 12. 2 to the power of 12. No, it's not 12, it's 13. There we go. So 2 to the power of 13 is equal to 8,192, which is equal to 0x200. Bam. So 12, that's easy, it's 4096, I know that off the top of my head. And then this would be same value here. Except for a 2, we're going to have a 1. And then 64, that's pretty easy. So 2 to the power of 1 is 2. So it's 1 is 2, 4, 8, 16, 32, 64, 6. And then you have 1, 4, which is 0. Then you have a 2, which would be, I think, 2. And then I'll put the 0x on that. Because 2 would be the value 1, 0. And then 1, 2, 3, 4, 0, 0. And then you have 1, 2, 3, 4, 5, 6. To the power of 6, yeah, I think that's right. So let's test that. We say 6, sorry, 2 to the power of 6 is equal to 64, which is equal to 0x 20. Oh. Did I mess up? Okay, I messed up the 20. So this would be 0. This would be 1. This would be 2. 1, 2, 3, oh, I forgot the 0 here. Right? So this would be 1, 2, 4, 8, 16, 32, 64. So that's going to be a four. There you go. Oops. Alright. Do away with that now. And then we got 1, 0, 0, 0, 0, 0. So that converts to 1, 2, oops, I need more zeros here. 1, 2, 4, 8. 8, so sorry, there's people next door banging. I'm doing construction. Super annoying. Oh, I just want to scream at them. Oh, it's so annoying. Okay, so it's 2 to the power of, if you have a 1 bit here, you have 2 to the power of 1. No, 2 to the power of 0. So it's a 0 to the power of 1, 2, 3, 4, 5, 6, 7, 8. So it's 2 to the power 8. And then 2 to the power 8, just represented, it's going to be 0, 1, 2, 4, 8, 16, 32, 64, 128, 256. That makes sense because it's the value right after 1 byte. Okay. So we got 2 to the power of 8 is equal to 256, which is equal to 0x100. Okay. All right, that table's done. Converting between decimal and hexadecimal representations requires using multiplication or division to handle the general case. To convert a decimal number x to hexadecimal, we can repeatedly divide x by 16, giving the quotient q and a remainder r, such that x is equal to q times 16 plus r. We then use the hexadecimal digit representing r as the least significant digit and generate the remaining digits by repeating the process on q. As an example, consider the conversion of decimal so-and-so. So we say that's a so-and-so times 16 plus 12. So just keep on dividing. That's what I used to do. I used to divide by, not 16, I would do like, I would have the numbers, to say we had this like number here, and I would just have the table, or I would lay out binary digits for all these things. So 1, 2, 3, 4, It says 2 to the 0, 1, 2, 3. 7, 6, 5, 4. Would this be 11 or 9, 8? We'll do it like that. So if I had a number like 125, I would go into here and I'd pick the closest to this. So that'd be 1, 2, 4, 8, 16, 32, 64, 128. Too much. So I say hit 64. That means that there's 1 here, and then I'd subtract off 64. And that'll leave me with 5 minus 4 is 1. Oops. And 12 minus 6 is 6. So we have 61 remaining. And that'll do it again. So that'd be 1, 2, 4, 8, 16, 32. So obviously 32 is the next one. So minus 32 from that. And we would get what? That'd be what? 11 minus 2 is 9. That's now 5. Minus 3 is a 2. 29. Then do it again. So say 1, 2, 4, 8, 16. So we say minus 16. That would give us what? 19, 6 from 19. No, 6 can go from 9. So that'd be 3. And 2 minus 1 would be 1. And then you got, so it's 64, 32, 16. And now we got 4, 8. So 8 is going to be the largest. 8 is removed from that, which gives us what, 5? So that'd be 8, 4, and 1. So if I do bin of 1, 2, 3, 1, 2, 5, should be 1, 1, 1, 1, 1, 0, 1. 1, 1, 1, 1, 1, 0, 1. So I used to do it that way. And it works up to a certain degree, but like you get up to like the higher powers, and I'll just use a dot to represent those. I just don't know those powers up there. So it's 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8,000 something, 16,000 something, 32,000 something, and then 65,564, I think it is. 655 something something. Yeah, I mean, I start like above here. I don't really know very well. Anyways, delete all this. So he's proposing a method here where instead of dividing by power, or instead of subtracting by powers of 2 and putting those bits in to convert to decimal, he just does this thing where he divides by 16 subsequently times and just adds onto that. Converting between decimal and hexadecimal representations requires using multiplication or division to handle the general case. To convert a decimal number x to hexadecimal, we can repeatedly divide x by 16. Giving a quotient q and the remainder r, such that x is equal to quotient times 16 plus r. Okay. Then use the hexadecimal digit representing r as the least significant digit and generate the remaining digits by repeating the process on q. As an example, consider the conversion of decimal so-and-so. But is it... Okay. So it's C2B, C4. Okay, and that reads out that way. From this, we can read off the hexadecimal representation. Conversely, to convert a hexadecimal number to decimal, we can multiply each of the hexadecimal digits by the appropriate power of 16. For example, given the number so-and-so, we compute its decimal equivalent as 7 times 16 to the power of 2 plus 10 times 16 plus 15. It's just a lot of arithmetic that the computers can do for me. I don't really feel like I need to do it. But apparently they want you to do it as practice here, so I'm gonna do it as practice. Why not? I'm just gonna copy this table down here, even though... How did that come through? Okay, this is now gonna be something called decimal. This is gonna be something called binary. This could be something called hexadecimal. Hexadecimal. And then we need to pad this guy out. Okay. And then we'll just delete all these. Okay, we got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So that gives the decimal 0. Binary 0. Hexadecimal is going to be 0x0. I would say that's right? Fuck off with that stuff, man. This help thing is the most annoying shit in the world. Okay. Practice problem 2-3. A single byte can be represented by 2 hexadecimal digits. Fill in the missing entries in the following table, giving the decimal, binary, and hexadecimal values different byte patterns. Okay. 1, 2, 3, 158, 76, 145. Binary. Okay. 1010 1110, and then 0011 1100, and then 111 0001. I don't know why, but I really like doing this. I mean, it's kind of like brain dead stuff, but like I kind of like doing it. It's kind of fun. Okay, and then you're gonna need to be like that and like that. Okay. 158. So I'll use this area down here as a scratch pad. So 158 will be 1 from the 256 column. Or sorry, 1 from the 128. So we're gonna subtract off 128 from 158. And of course, that's going to leave 30 behind. Then we're going to subtract off. We're going to subtract off. 30 would be a 16, which will be a 4 here and a 1 here. And then the next value would be an 8, which will be a 6. And then the next value would be a 4, which will make this a 2. And then the next value will be a 2. So that's our digits here. So 128, skip to 64, skip to 32, have a 16, have an 8, have a 4, have a 2, and a 0. So if we do this, this should equal 158. So that's our binary. Oops. If we chunk it appropriately like that, that's what we put in here. Okay, and then our hexadecimal representation, we could just take this back. I don't need this anymore. And we're going to say, hey, and here, that's 9. And the other value is going to be E. If we do 0x9e, bam. Zero x9e. Look at that. Beautiful. All right, so now we got 76 going on here. So 76. We have to indent this a little bit. So obviously going to minus a 64 off of that. That's going to give us what? A 16 minus 4. No, 6 minus 4, which is 2, and that'd be 12. And then we're going to subtract off from that an 8 and a 4, which will leave us with a 0. 12. Yep. So to read that out, it'd be 64, skip 32, skip 16, 8, 4, 2, 1. So if you want to do the full binary, it'll be like that. And we can verify that. 0b, that. Oops. 76. So I'm just going to yank that and put it over here. Now to get the hex on that, that's going to be 8 and A. No, that's not 8. What are you talking about? 1, 2, 4. It's going to be 4. And then A. Yeah. Is it an A? No. That is 1 and 2, which would be 3. That's a C. Because 1, 1 would be 8 plus 4, which is 12. A is 10, 11, 12. A, B, C. Yeah, 4C. Zero x 4C. Yep. Okay. Next one, 145. 145. We're gonna minus a 128, and then that's gonna give us back what? 2 and that'll be 7 here. This goes down to a 3, so that'd be a 1 here, and that's 0. So we got 17. And then this is going to be minus 8, which will give you back 2 and 7 is 9. Give me back a 9. And then we can't get to 9. Hold on a second. I think I messed this up. So 145, 128, 5, so that'd be 15, 8, 7. 3, 2, 1. So it's definitely 17. Oh, there's a 16. I can minus a 16. There we go. So that leaves back a 1. And then, of course, that's a minus 1. So this will be 128, 64, 32, 16, 8, 4, 2, 1. Should be like that. Let me just 0B up this. 145. That checks out. And we will put it right in here. And if we wanted to do the same thing, I'll just do it in line here. So this is going to be obviously a 1. And that's going to be 8, 9. So it'd be 91. 0x 91. If you go down here, 0x 91. Bam. Alright, so now we got the opposite here. We have the binary. We want to go to hexadecimal and decimal. I can do some of these in line. I guess they're all gonna be limited to 2 characters, so I can just say hex here. That'll like shorten this a little bit, keep it a little bit more compact, like that. There we go. We fill in these as 0x, and then this can just be, say, decimal. And we can take away all of these. There we go. Look at that. Looks much cleaner. So, to fill this out, so that's going to be an A. 0xa. Right? Because you got 8, then 9, and then A. Yeah. This is going to be an F. That's an easy one. That's a 3. That's a 1. That's an obvious, 8 plus 4 would be 12. So that's going to be C, I think. 10, 11, 12, ABC, yeah. And then this is going to be E. Because it's F minus 1. So I'll just check the, I'm not going to check these quite yet. So I want to check them as I convert the. So this is going to be. So you got 1, 2, 4, 8, 16, 32, 64, so 128 plus 32 plus 8 plus 4 plus 2. So I just stack these. Oops. Come on, what are you doing? Sometimes lazy Vim is just like trying to be too helpful. It's like, dude, I do not need you to insert a table here. Okay, so 8, 9, 10, so that's 24. So I'll put a 4 here. Oops. Carry the 2. So that's 7. 7 there. So it's 174. Let's test that out. 0B 10101110. 174. So I got that right. 174. And then if I do 0xAE, 174. Great. Easy peasy. Next one. So 32. Come on, why are you doing that, bro? 32, 16, 8, 4. So that's going to be 8, 9, 10, 16, 20. So it's 0, carry the 2. 3, 4, 5, 6. This would be 60. in decimal. 60. Okay, so we say 60 is equal to 0b 00111100, which is equal to 0x3c. Got it. All right, the next one is going to be 128 plus 64 plus 32. Come on. Why? 32 plus 16. That's all the higher order bits. And then plus 1 at the end. So that's going to result in 8, 9, 10, 11, 12, 13, 14. Sorry, I'm doing this in my head. This would be 8, 9, 10, 21. So it leaves the 1 down here. You then carry the 2. Oops, go away, please. Carry the 2. 6, 9, 10, 14. R4, R1, and then you R1 down here. 141. So let's check this. 141. 141 is equal to 0b 11110001, which is equal to 0xf1. Oh Lord. Did I mess something up? $128, 64, 32, 16, and then 1. 8, 2, 10, 21, carry the 2. Then we got 10, 13, 14, carry the 1. Oh, it's 241. Forgot to add my last column there. My bad. I always make silly mistakes like that. That's why I always double check my work, validate things, because I make so many careless mistakes. I've always been that way. Okay, that makes sense. Alright, so I did all those. Okay. So we got an aside. Converting between decimal and hexadecimal. For converting larger values between decimal and hexadecimal, it is best to let a computer or calculator do the work. There are numerous tools that can do this. One simple way is to use any of the standard search engines with queries such as convert so-and-so to decimal. Thank you. Can I do that here? Or are you asking me to do it by hand? I don't know. It is. I do enjoy revisiting this stuff occasionally. Okay, so we basically just have 3 more entries in this table that wrapped onto the other page that I'll take care of here. Okay, so 0x75. And then 0xbd, and then 0xf5. Okay, for these, I'll take this, convert it into binary first. So you got 7, which is going to be 0, 1, which is 4, 5, 6, 7. Yeah. And then 5, which is 0, 4, 0, 1. Yeah. So that's the binary representation. And then the decimal is going to be, this will be 64 plus 32 plus 16 plus 4 plus 1. So you got 10, 16, 17, 7, carry the 1 up here, 6, 10, 11, so 117. So 117 is equal to 0b 0, 1, 1, 1, 0101, which is equal to 0x75. Okay, next one, 0xbd, which is going to be equal to b 8 9 10 11 12. So this would be C. This would be A, and this would be B. So that's B. And then this is F. E. D would be that. So let me just make sure this one is correct. 0B 1011 1101 is equal to 0xbd. Yeah, that's true. And then, oops. Take that, and it's going to be 128 plus 32 plus 16 plus 8 plus 4 plus 1. So let's align these things. And we got 10, 16, 28, 29. Put a 9 down, carry the 2. So it's 4, 5, 6, 7, 8 here. So go to 8 there, and then 1. 189. Oh, I did an assignment, damn it. There we go. Okay. And then we got 0x f5, which f is just all ones, 5 is 0, 1, 0, 1. It's 4 plus 1. And then to convert that to decimal, it's going to be 128, 64, 32, stop it, 32, 16, so that'd be all the high order bits. And then we got a 4 remaining and a 1 remaining. So that's 8, 10, 20, 4, 25. 5 there, 2 there. 6 and 4 is 10, 13, 14. Put a 4 there, put a 1 there, and then we got 2. So 245. 245, and all this. Paste it there. Say 245 is equal to 0b1111 0101, which is equal to 0x f5. Bam. I think the hardest operation is converting from decimal into binary notation, because binary decimal into binary or hex. Once you're in binary or hex, it's easy to convert back and forth, and it's sort of easy to convert from that representation into a decimal representation, but converting from decimal to binary requires division. I guess you can do a subtraction as well, but the most effective way is to do it through division, and I don't know, I'd rather just have a calculator do it. Okay, so now we're on practice problem 2.4, 2.4 dots. It also has a table. No, it just has an A, a B, a C, and a D. And here it says, without converting the numbers to decimal or binary, try to solve the following arithmetic problems, giving the answer in hexadecimal. Hint, just modify the methods used for forming decimal. Yeah, that's what I was going to do. So we have 605C plus a 5 over here, and that's going to equal, I'll put a little plus sign here to indicate that is a plus. So that's going to equal, well, 5 and C, D, E, F. So you subtract away 3, so we're at F. So rolling over, now we're at 1, 0, and then it'll be a 1 here. Because 0xc plus 0x5 is equal to 1, 1 in hex. So I have to say hex underscore hex. What the hell? How is that BD? Yeah, it's 1, 1. So I got 17 out, and then when I convert 17 into hex, it said BD? Why? I don't understand how that 17 came out, and I said, hey, convert that to hex, and it gave me BD. What is it, BD? 0x BD. It's 189. That is bizarre. That is like Python. Let's try it again. 0xc plus 0x5 hex underscore. I've never seen that before. Can you explain to me why Python evaluated hex of underscore to be 0x BD when it should have been 0x 1, 1? I am using the standard Python REPL. Well, we'll just kill Python. Try it again. 0xc plus 0x5 17 hex of underscore. Did I assign into underscore at some point in this session? Oh, I assigned into underscore, that's why. Okay. That's why I must have messed that up. Because I was trying to do a comparison and I did an assignment. That's why I forgot about that. Alright. My bad, my bad. I knew there was something wrong on my end. Let me scooch back my desk here because the light's starting to blind me. Okay. Anyways, we're doing some stuff here. So 5 and C came 11. 5 and 1 is just 6. And this becomes 6, 0. Yeah. And if I can validate that, 0x 605c plus 0x5 is equal to 0x 6061. Cool. Then B here is going to be 605c minus 20 20 and this is going to be a minus operation. So we do, okay, C minus 0 is equal to C, and then 5 minus 2 is equal to 3. That wasn't hard. So if we use 0x, 605C minus 0x 20 is equal to 0x 603C. Okay. Be nice if it get a little harder than this. So now we have 605C plus 32. So plus is the operator here. 32. So C and 2, so DE. And then 5 and 3 is 8. And then you got your 60. 60. These are pretty easy. So 0x 605C plus 0. Oh, it just says 32, not 0x32. So I need to go back here. I need to convert 32. So it'd be 1. So we got 1, 2, 4, 8, 16, 32. 1, 2, 4, 8, 16, 32, yeah. And if you convert that into hex, it would be 2, 0. So this becomes 2, 0, in which case C is the same thing. So 0x20, 32, so we'll just, oh no, it's adding 20 this time, so subtract 20. So C plus 0 is 0, that'd be a 7 here, and a 60 here. Okay, and we'll just validate from the book. 0x 605C plus 32 is equal to 0x 6070. For adding 32, which is 2, 0. Oh, sorry, C. I meant to put a C here. 0x 607C. There we go. And then down here, D is 60FA minus 605C. That's going to result in A minus C. We're going to have to borrow from this. So that turns F into a, we get a 1 out of that. And F now becomes E. Now it's 1A. Is that how you do it? 2. So 1A minus C. So it'd be D, E, F. Okay. What is the C from 1A? We can take the A out, A, B, C. So there's 2 left over from 1, which would be an F and an E. So it come out as an E here. I have E minus 5, which would be 9, plus 5 would be A, B, C, D, E. So this would be a 9. And then this would just be zeros because they subtract out. So 9E, I think. Let's try that. 0x60FA minus 0x605C is equal to 0x9E. Sorry, syntax error. Meant to do a minus. Okay, Nova mode there. Okay, got it. Sweet, sweet, sweet. All right, so I got all those. Next, onward, data sizes. Every computer has a word size indicating the normal size of pointer data. Okay, we got plenty of pages to read here and code to read. And then we got some practice problems at page 82. And then some more in 91. Some more 94. Oh, we're not even at integer representations here. There's so much content here. Oh, wow. Chapter 2 goes all the way, it goes hard. The reading itself with practice problems goes all the way to 163. So we're not going to finish this chapter anytime soon. All right, I'm going to take a quick break here, and I'll be back in a minute. I can't believe there's so much content on integer, or data representations. And this instructor had the nerve to say just read each chapter 3 times. It's like, bro, these chapters are not short. I guess the reading, I could read the chapters 3 times. Reading and doing the problems, I guess, is the other thing. All right, let's continue reading. Data sizes. Every computer has a word size indicating normal size of pointer data. Since a virtual address is encoded by such a word. The most important system parameter determined by the word size is the maximum size of the virtual address space. That is, for a machine with a W-bit word size, the virtual address can range from 0 to 2 to the power of W minus 1, giving the program access to at most 2 to W bytes. In recent years, there has been a widespread shift from machines with 32-bit word sizes to those with a word size of 64 bits. This occurred first for high-end machines designed for large-scale scientific and database applications, followed by desktop and laptop machines, and most recently for the processors found in smartphones. A 32-bit word size limits the virtual address space to 4 gigabytes. That is just over 4 times 10 to the 9 bytes. Scaling up to 64-bit word size leads to a virtual address space of 16 exabytes, or around 1.84 times 10 to the 19 bytes. Most 64-bit machines can also run programs compiled for use on 32-bit machines, a form of backwards compatibility. So, for example, when a program prog.c is compiled with the directive gcc m32 prog.c, then this program will run correctly on either 32-bit or 64-bit machine. On the other hand, a program compiled with directive M64 will only run on a 64-bit machine. We'll therefore refer to programs being either 32-bit programs or 64 bits programs, since the distinction lies in how a program is compiled rather than a type of machine on which it runs. Computers and compilers support multiple data formats. Let me bring my reading light back over here. Computers and compilers support multiple data formats using different ways to encode data, such as integers and floating points, as well as different lengths. For example, many machines have instructions for manipulating single bytes, as well as integers represented as 2, 4, and 8 byte quantities. We also support floating point numbers represented as 4 and 8 byte quantities. The C language supports multiple data formats for both integer and floating point data. Figure 2.3 shows the number of bytes typically allocated for different C data types. We discuss the relationship between what is guaranteed by the C standard versus what is typical in section 2.2. Exact numbers of bytes for some data types depend on how the program is compiled. We show the size for typical 32-bit and 64-bit programs. Integer data can be either assigned, able to represent -0 and positive values, or unsigned, only allowing non-negative values. Data type char represents a single byte. Although the name char derives from the fact that it is used to store a single character in a text string, it can also be used to store integer values. Data types short, int, and long are intended to provide a range of sizes. Even when compiled for 64-bit systems, data type int is usually just 4 bytes. Data type long commonly has 4 bytes in 32-bit programs and 8 bytes in 64-bit programs. Okay, if we go back over here, so you have char. Most people assume char is signed by default, and it is on some architectures, but it's not guaranteed by the language. Unsigned char. Okay. Sorry, I didn't read this. Typical size in bytes of C data types. The number of bytes allocated varies with how the program is compiled. This chart shows its values typical of 32-bit and 64-bit programs. Declaring pointers. For any data type T, the declaration T star P indicates that P is a pointer variable pointing at an object of type T. For example, char star P is a declaration of a pointer to an object of type char. To avoid the vagaries of relying on typical sizes and different compiler settings, ISO C99 introduced a class of data types where the data size is fixed regardless of compiler and machine setting. Among those data types are, I think these are in standard int, int32t and int64t, having exactly 4 and 8 bytes respectively. Using fixed size integer types is the best way for programs to have close control over data representations. Most of the data types encode signed values unless prefixed by the word unsigned or using a specific unsigned declaration for fixed size data types. The exception to this is that to this data type char. So the exception is that to this blah, blah, blah. All right. The exception to this is data type char. Although most compilers and machines treat this as signed data, the C standard does not guarantee this. Now I'm going to highlight this because I think it's important. Instead, as indicated by the square brackets, the programmer should use the declaration signed char to guarantee a 1 byte signed value. In many contexts, however, the program's behavior is insensitive to whether the data type char is signed or unsigned. The C language allows a variety of ways to order the keywords and to include or omit optional keywords. As examples, all the following declarations have identical meaning: unsigned long int, long unsigned int. We will consistently use the forms found in figure 2.3. Figure 2.3 also shows that a pointer, e.g. a variable declared as being of type char star, uses the full word size of the program. Most machines also support 2 different floating point formats: single precision declared as a float and double precision declared as in C as double. These formats use 4 and 8 bits respectively. Programmers should strive to make their programs portable across different machines and compilers. One aspect of portability is to make the program insensitive to the exact sizes of the different data types. The C standard sets lower bounds on the numeric ranges of different data types. As well as will be covered later, there are no upper bounds except when the fixed size with fixed size types. Sorry, let me reread that. The C standard sets lower bounds on the numeric ranges of the different data types, as will be covered later, but there are no upper bounds except with the fixed size types. With 32-bit machines and 32-bit programs being the dominant combination from around 1980 until around 2010, many programs have been written assuming the allocation listed for 32-bit programs in figure 2.3. Okay. With the transition to 64-bit machines, many hidden word size dependencies have arisen as bugs in migrating these programs to new machines. For example, many programmers historically assumed that an object declared as type int could be used to store a pointer. This works fine for most 32-bit programs, but it leads to problems for 64-bit programs. Addressing and byte ordering. For program objects that span multiple bytes, we must establish two conventions that the address of the object will be. Two conventions. What the address of the object will be and how we will order the bytes in memory. In virtually all machines, a multi-byte object is stored as a contiguous sequence of bytes with the address of the object given by the smallest address of the bytes used. For example, suppose a variable x of type int has the address 100, 0x100, that is the value of the address expression ampersand x is 0x100. Then, assuming data type int has a 32-bit representation, the 4 bytes of x would be stored in memory location 0x100, 101, 102, 103, yeah. For ordering the bytes representing an object, there are two common conventions. Consider a w-bit integer having bit representations, where w minus 1 is the most significant bit and 0 is the least. Assuming w is a multiple of 8, these bits can be grouped as bytes, with the most significant byte having bits so and so, the least significant byte having bits so and so, and the other bytes having bits from the middle. Some machines choose to store the object in memory order from least significant byte to most. I think that's little endian. And that's the one that x86-64 uses, while other machines store them from most to least. The former convention where the least byte comes first is referred to as little endian. The latter convention where the most significant byte comes first is referred to as big endian or network endian. Suppose the variable x of type int. And at address 100 has a hexadecimal value of. Okay. Wouldn't that be 4 bytes? Okay, so suppose the variable x of type int and at the address 100 has a hexadecimal value of so-and-so. Okay. The ordering of the bytes within the address range 0x through 3 depends on type of machine. So little endian would have the right. Yeah. Note that the word so-and-so, the high order byte, has hexadecimal value 0x01, while the low order byte has value 0x67. Most Intel compatible machines operate exclusively in little endian mode. On the other hand, most machines from IBM and Oracle arising from their acquisition. Boom, boom, boom. Wait a minute. Did I already skip? Right, arising from their acquisition of Sun Microsystems in 2010, operate on big endian mode. Note that we said most, the conventions do not split precisely along corporate boundaries. For example, both IBM and Oracle manufacture machines that use Intel compatible processors and hence are little endian. Many recent microprocessor chips are big endian, bi-endian, meaning that they can be configured to operate as either little or big endian machines. I didn't know that. In practice, however, byte ordering becomes fixed once a particular operating system is chosen. For example, ARM microprocessors used in many cell phones have hardware that can operate in either little or big endian mode, but the two most common operating systems for these chips, Android and iOS from Apple, operate only in little endian mode. People get surprisingly emotional about which byte ordering is the proper one. In fact, the terms little endian and big endian come from the book Gulliver's Travels by Jonathan Swift, where two warring factions could not agree as to how a soft-boiled egg should be opened, by the little end or the big. Just like the egg issue, there is no technical reason to choose one byte ordering convention over the other. and hence the arguments degenerate into bickering about socio-political issues. As long as one of the conventions is selected and adhered to consistently, the choice is arbitrary. For most application programmers, the byte ordering used in their machines are totally invisible. Programs compiled for either class of machine give identical results. At times, however, byte ordering becomes an issue. The first is when, well, we'll talk about that in a little bit here. Let's read the aside. Here is how Jonathan Swift, writing in 1726, described the history of the controversy between big and little endians. Lilliput and... Wait a minute. Am I reading this Gulliver's Travel? Okay. Lilliput and Blefuscu. Oh, I hate fictional names. It's people like why name your characters Blefuscu? Have, as I was going to tell you, been engaging in most obstinate war for 6 and 30 moons past, began upon the following occasion. It is allowed on all hands that the primitive way of breaking eggs before we eat them was upon the larger end, but his present Majesty's grandfather, while he was a boy going to eat an egg and breaking it according to the ancient practice, happened to cut one of his fingers, whereupon the emperor his father published an edict commanding all of his subjects upon great penalty to break the smaller end of their eggs. The people so highly resented this law that our histories tell us there had been 6 rebellions raised on that account, wherein one emperor lost his life and another his crown. These civil commotions were constantly fomented by the monarchs of Blefuscu, and when they were quelled, the exiles always fled for refuge to that empire. It is computed that 11,000 persons have at several times suffered death rather than submit to break their eggs at the smaller end. Many hundred large volumes have been published upon this controversy, but the books of the big Indians have been long forbidden, and the whole party rendered incapable by law of holding employments. In his day, Swift was satirizing the continued conflicts between England, Lilliput, and France, Blefuscu. Danny Cohen, an early pioneer in networking protocols, first applied these terms to refer to byte ordering, and the terminology has been widely adopted. Boom, 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 boom. Who cares? Why did I even read that? Okay. So now we're talking about, at times, however, byte ordering became an issue. The first is when binary data are communicated over a network between different machines. A common problem is for data produced by little endian machines to be sent to a big endian machine or vice versa, leading to bytes within the words being in reverse order. For the receiving program to avoid such problems, code written for network applications must follow established conventions for byte ordering to make sure the sending machine converts its internal representation to the network standard, while the receiving machine converts the network standard to its internal representation. We will see examples of these conversions in chapter 11. So that's when we have to use the stupid get adder info and network to string to network and network to string, those functions. Okay, boom, 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 boom. Yeah, all the C networking stuff around address resolution and opening up sockets, adders in general, they're all big endian. And you have to represent them in your memory as big endian, even though you're on a little endian machine. It's kind of weird. All right, a second case where byte ordering becomes important is when looking at the byte sequences representing integer data. This occurs often when inspecting machine-level programs. As an example, the following line occurs in a file that gives the text representation of machine-level code for an x86 64 processor. So we're at memory just so-and-so. and these are the bytes. The line was generated by a disassembler, a tool that determines the instruction sequence represented by an executable program file. We'll learn more about disassemblers and how to interpret lines such as this in Chapter 3. For now, we simply note that this line states that the hexadecimal byte sequence 015043-0B2000 is the byte level representation of an instruction that adds a word of data to the value stored at an address computed by adding this immediate value to the current value of the program counter. The address of the next instruction to be executed. I'm gonna get something to snack on. I think I might just take a break here, and get some food from the grocery store. Maybe even eat dinner, an early dinner, because I have a thing tonight, a social thing I have to go to. So I'm gonna take a break here, and I will mark where I'm at in the book. So we'll just pick up on this instruction here. I get what he's talking about already, because when you print out the bytes in the order from 0 increasing left to right, they're kind of jumbled, because we're used to reading left to right where the most significant bit is first. Most significant byte, I should say, is first. But when you print them from 0 upwards on a little endian machine, you're printing the least significant byte first, and so it's going to be on the left hand side. And that's just an artifact of the printing, though. I mean, you can reverse that. That's not anything. I like little endian better than big endian. All right, so I'll take a break here, and I will be back in probably about an hour and a half, maybe, just to get some dinner and chill for a little bit.